So we went over the 8 definitions that a vector space should satisfy. A vector space is a set with n set of numbers, so it's called scalar. So you have a vector space and scalar, and these things have operations called vector addition and scalar multiplication, and they must satisfy these properties. And anything that satisfies this is called a vector space, and I kind of wanted to elaborate why we want to make it abstract, and showed you that even the story of the Fourier series that we use for solving partial differential equations, that's in the domain of linear algebra. The set of continuous periodic functions over an interval, they form a vector space. It's very surprising. We can actually use that fact to do a lot of things. Right? Fourier series is used in everywhere. I mean, since you guys are engineers, you've seen it in action in many places, right? So, so that's a good reason why we want to learn linear algebra. Now, I don't want to spend time going through every little bitty proofs, because for engineers, we really don't need them. But I do want to show you a few, just to show you how things can be proved out of some basic properties. And it's sometimes fun seeing something so obvious being proved using basic properties. So let me show you a few things. So for example, number 1, 0 times v is 0. That's so obvious, right? But even this, I need to say a little bit. This is a number, so this is a scalar. This 0 right here, scalar 0. So it could be inside the complex numbers or the real numbers. And this is a vector 0. It's hard to see it when I write it on the board, but usually in the textbooks they write vectors as boldface. So this will be boldface, and this will be boldface. Okay? And now that doesn't look that obvious, or still? I don't know. Yeah. Okay. But let's try to prove it. Right? So how do we prove that? Well, we use this property right here, number 5. So we say 0 plus 0, v is equal to 0 times v plus 0 times v. Okay. But 0 plus 0, this is just addition of two real numbers. So that has nothing to do with vector space. 0 plus 0 exists even before we define what a vector space is. So 0 plus 0 is obviously 0 just from the domain of real numbers. So we have the following. 0v equals to 0v plus 0v. Now, we also have in rule number 4 that if you have any vector and its inverse, there should be an additive inverse vector that gives you 0. So this number 4, I didn't write down the full story, but this really means for any vector there exists an inverse vector, okay? Additive inverse of that vector. So what I can do is, now I can say, if I have a vector 0v and then plus the additive inverse of 0v, right? Then this must be same as, since I said this is same as this, I can replace this by 0v plus 0v plus negative 0v, right? So here, these are the same thing. But then now, look at what this is. According to rule number 4, this is 0, isn't it? But again, this is 0 as a vector, okay? 0 as a vector. And then here we can use the associativity, and instead of doing this plus this and then this, we can add these two first, right? And then using the associativity here, number 2, we can add these two. And because we are again adding a vector by its inverse, item number 4 says that you're adding 0. Well, what is 0? Well, 0 is an additive identity, right? So 0v plus 0, according to this property number 3, is v itself, right? So 0v itself. So this is equal to just 0v. So now I've proved that 0v is 0. Wow, so much work and a lot of rules just for an obvious thing, right? But yeah, it has to be done. So if you look at very abstract kind of linear algebra books, you will see a lot of proofs like this, like pages after page, obvious stuff being proved. With like, sometimes it's harder than it looks, yeah. But it's done. Yeah. And in fact, yes.
Might be a dumb question, but
Yeah.
is there like a mathematic proof for 0?
So mathematicians quickly realize that not all things can be proved. So you always start with some system of axioms. So you define something. Right? So let's say we have these properties that we want. Okay? If you define it, and then using those axioms, we prove something further.
So those are considered axioms.
Yeah, these are considered as the axioms for a vector space. So there are axioms for geometry, there are axioms for numbers, and there's always a yearning for something more fundamental. Like, can you reduce the number of axioms so that we can have the least that's needed and then prove everything else? And people who work on that are called logicians. And we also know that not everything can be proved. That's another strange thing. So in the beginning of the 20th century, around the time when Einstein came up with the revolution in physics, there was a mathematician named Kurt Gödel who also proved that there are true things that cannot be proved in math. You can have a true statement where no proof exists. And then another thing that he proved was that there could be, you could have a system of axioms, but there, there's a system of axioms, but there's no way to know beforehand that the axioms might have contradictions between them. So those kind of made a very alarming response from the mathematicians, because they started questioning, like, are what we're doing even meaningful, right? If we don't know if some things have contradictions, but we still do it anyways. Yeah.
So do all those axioms, are those all be able, like, can you prove all of those axioms, or some of them are just like?
No, these are just requirements. If you give me a set, and you give me a set of numbers, so real numbers in a set, and
Oh no,
I'm getting sick again. All right. So if you give me a set, and then what I do is I just check each property, and if it doesn't satisfy any of the properties, then we say it's not a vector space. If it does satisfy all the properties, then we say it's a vector space. So it's a bit different. True axioms are like, you can't even check anything, it's just saying. If you look at really, really fundamental math books, there's something like, there exists a null set. That's one of the axioms. Like, the null set, the set with no elements in there, we accept that such a thing exists. Something like that. Very, very, it's very abstract, I think. Yeah. Okay, but anyways, so we have this. Now let me show you another one. I want to show you that -1 times v is equal to negative v. Okay. Again, it really seems obvious. Right? but they have different meanings. So here, -1 is a number, and you're multiplying it to a vector, right? But when I say negative v means it's the additive inverse of v. That's what it means. Okay? So to prove this, what I need to show is that this acts like a negative v. So if you have v and you add -1v, that should give you 0. If this is true, right, then we've proved it. All right, so let's prove it. How do we prove it? Well, let's see. Let's say you have v plus -1v. Now this last item here says 1 times any vector is same as itself. It's an identity of multiplication. 1 times v is same as v. And then we can use this rule, rule number 6, to factor. No, it's not that one, sorry. It's rule number 5. We can factor the u. So we're applying rule number 5 in the reverse direction. Okay? So I can do 1 plus -1v. And then what's that? 1 plus -1. That's 0, but because that's in the domain of real numbers. Okay, that just holds without referring to vector space anyway. But then we just proved that 0v is what? 0. It's done. We show that this acts like the inverse. Now, if a mathematician was watching me do this, they might point out one more thing. This still doesn't prove why this is same as that. There's one more thing I need to prove, which is that the additive inverse of a vector is unique. Okay, that's something. Only then I can say, hey, this acts like an inverse, and because there's only one additive inverse, this must be same as that. So I actually need to prove another one. So it's really not the end of the proof. So let me write down this third one, which is that additive inverse of v is unique. So what is this statement saying? It's saying that if u plus v is 0 and u plus w is 0, then this must mean that v and w must be the same, because they add to 0. That means v is a additive inverse of u, and w is also an additive inverse of u, and therefore v and w should be the same. That's what I'm trying to prove. Need to prove, yeah, this thing. All right, so let's prove it. So this is the given one, right? So what we do is consider v plus u plus w. You see where I'm going with this? All right, so first, v plus u plus w is v plus u plus w. This is what it means. If there's no parenthesis, it means that the parenthesis is in the first one. But addition is commutative. This is the first property I wrote. Oh, but what did we decide? The given is that u plus v is 0. And 0 plus anything is?
0. Oh, sorry.
Itself, w. Okay. But then, now I'm going to say v plus u plus w is equal to v plus u plus w. Well, what is this property? This is the associated property, number 2. And then what's u plus w? 0. What's v plus 0? Oh, so these two are the same, so these two must be the same. Done. That's the proof. quite neat, right? Yeah, it's kind of fun trying to prove really obvious things.